All right, let's begin with a problem like this. So we have two capacitors that are in series here, hooked up to a voltage source. The voltage source has voltage of 10 volts. Capacitor 1 is 7 microfarads and capacitor 2 is 5 microfarads. And what I want to know is what is the charge on C1. So I hook this thing up and ultimately there's going to be a charge buildup on C1. The question is, what is that charge? Well, in order to answer that, I'll probably figure out a lot of other things along the way. For example, almost always when you have a problem like this, you have to find an equivalent capacitance. So let's go ahead and get started and see if we can do this problem. If I combine these two capacitors together, then this becomes a problem that looks like this. This one capacitor here, and you can call this whatever you want, but I'll call it C12. And since these are in series, to get C12, I have to do a little bit of math. So 1 over C12 is going to equal 1 over C1 plus 1 over C2. Now that's the one way to do it. Remember, if you're combining just two capacitors together, though, you can do product over sum. So C12 is going to be C1 C2 over C1 plus C2. So that's going to be 7 microfarads times 5 microfarads divided by C1 is 7 microfarad plus 5 microfarad. So that's going to be 35 over 7, 8, 9, 10, 11, 12. And the units, you see these microfarads on bottom are going to cancel one of those, and we're left with units of microfarad. So 35 divided by 12, 35 divided by 12 is 2.917 microfarad. All right, so if this is still V0, then the charge that's on this can be found as Q, let's call it Q12, is going to be C12 times the voltage across that. And since we only have one voltage source here, that's just going to be V0. So C12 is 2.917 microfarad multiplied by V0, which is 10 volts. And now it's 29.17. And the unit is going to be coulombs, but we've got this micro here, so that's going to be microcoulombs. So there's the charge that is on C1. Now, you might say, well, we just found the charge on this. How do I know that's the charge on C1? Because C1 and C2 have exactly the same charge. And that charge is going to be whatever the charge is on this. And one way to think about this is to imagine that the plates here are spread apart. And this portion right here is just inserted in between. That big eye right there is inserted in between. So when you pull that plate that way and this plate that way, then that top plate becomes this and the bottom plate becomes this. So the charge on those plates are going to be the same. The presence of, say, a positive charge up here induces a negative there, which induces the positive there, and you already had the negative there. Okay, so that's the charge that's on this, as well as the charge that's on C1. And because these are in series, it's also going to be the charge that's on C2. All right, so we have pretty much solved this problem. That's the charge right there that's on C1, so we could call that Q1 is the same as Q2, is the same as Q12, and it is equal to 29.17 microcoulombs. All right, so we've done that problem. Let's do another one. Let's say we've got this problem right here. Now, we have actually worked in a previous video how to find the equivalent capacitance for an arrangement of charges that looks like this. And whenever we did that, we found the answer, but we can do it again here. What we're after in this case is I have 3 capacitors here. These 2 are in parallel with each other, and then that combination is in series with this 3rd capacitor here. The voltage of the battery is 12.5 volts, and you see here what the C1, C2, and C3 values are going to be. Now, the question could be worded in any number of ways. For example, I could say, what is the charge on capacitor 1 and the voltage across capacitor 1? But in the process, regardless of what you're asked for, we're going to figure all of these out. So let's just find them all anyway. Okay? So whenever we begin a problem like this, it's usually a good idea, unless you have practice and you can see exactly where you're going in a problem like this, it's usually a good idea to just start combining things together to simplify matters. So if I combine C1 and C2, that becomes pretty straightforward. And let's call that capacitor C12. And then you can see C3 is down here. And this is our voltage source. And C12 is just the sum of these two. So it's going to be equal to 17.3 microfarad. And then C3 is still 4.50 microfarad. And in this case, we have a problem that's very similar to the one we just worked, where we have 2 capacitors here that you can combine together, and you could figure out what the charge is on each one individually. So we've simplified the problem a little bit and made it a little simpler. Let's go one step farther and combine C12 and C3. And whenever we do that, we end up with a really simple situation of 1 capacitor and the battery. So we could call this C123 or C equivalent, whatever the case is. And C123 is going to be product over sum. So it's going to be 17.3 microfarads multiplied by 4.50 microfarad divided by 17.3 microfarad plus 4.50 microfarad. And whenever you do that, you end up with an answer of 3.57 microfarads. So that's the equivalent capacitance if I combine all of these capacitors together here. Okay, well, now that I recognize that, I can look at this and say, what is the potential or the voltage across capacitor 1? And I notice right away that whatever the voltage is across capacitor 1, it's the same voltage across capacitor 2 because these two are in parallel with each other. And whatever that voltage happens to be there, that's the voltage across this right here. I also know, just by observation, that whatever the voltage is here, plus the voltage here, that has to equal to the 12.5 volts for my battery. And then down here I notice, well, the voltage across this is 12.5 volts. So 12.5 volts is somehow split between these two right here. Okay, I should be able to figure that out. So just writing down my observations, things that I know at this point, I know that V1 is going to be the same as V2. All right, well, down here, I recognize that the charge across this is going to be the same as the charge in C12 and C3. So if I figure out this charge down here, I've got the charges of these two as well. So let's go ahead and do that. You know that the charge, let's call it the charge on this capacitor is Q123, is going to be C123 times its voltage, which is just V. So C123 is 3.57 microfarad multiplied by V, which is 12.5 volts. And that turns out to be, let me do that calculation, 44.625 microcoulombs. So that's the charge there. That's also the charge across these two capacitors. So Q12 is the same as Q3, and that is 44.625 microcoulomb. Now up here, that's the charge Q3, that's the charge across that. I could figure out the voltage from that now because I have the capacitance and I have its charge. So recognize that Q3 is going to be C3 times the voltage across 3. I know what Q3 is and I know what C3 is, so I can go ahead and solve for V3 out of that. And that's going to be Q3 over C3. Q3 is down here, 44.625 microcoulomb, divided by C3, which is 4.50 microfarad. Do that calculation, and let me see what we end up with. And I end up with 9.92 volts. Now that's the voltage across this, which is the same as the voltage across this. So the voltage here, V3, is 9.92 volts. Then the voltage across V12, voltage across this capacitor 1,2, is going to be this voltage, 12.5 volts, minus 9.92 volts. That turns out to be, let's see, is 2.58. So 2.58 volts is what that happens to be. So 2.58 plus 9.92 is the 12.5. That means 2.58 is what the voltage is across this combination here. So the voltage across, and we're running out of room here, so I'm just going to borrow this space right here. Voltage 1 across capacitor 1 is 2.58 volts. That's also the voltage across 2. Now, could I figure that out a different way? Yeah, probably so. But it's pretty straightforward to do it this way. But, you know, we need to be able to check all of our findings, so let's see if this works out. I found out that the voltage across 3 is that. I found out that charge across that is given here. The voltage is that. Let's go up here now. I know what the voltage is across these two. Let's figure out what the charge is across that. And this charge here should be the same as this charge down here. Okay, the charge across these two should add up to be whatever the charge is here. So I know what voltage 1 is. It's given by this. So what is charge 1? Q1 is going to be C1 times V1. C1 is 12.0 microfarad multiplied by V1, which is 2.58 volts. So Q1 turns out to be 30.96, and there's a micro coulombs there. Okay, now that 30.96, when I add it to whatever Q2 is here, should sum up to be 44.625. Well, let's do the Q2 calculation then. Q2 is going to be C2 times its voltage, but its voltage is the same as what it was for V1. So this is going to be C2 of 5.30 microfarad plus 2.58 volts. And that turns out to be 13.674 microcoulombs. Okay, let's add these two together and see what we get. Is equal to 44.634 microcoulombs. That is the same as that within the rounding errors. So we've found it. Now let's make sure that we found everything that was listed here. CEQ, well, that was down here. That's CEQ right there. Q1, well, Q1 is that right there. Q2 is that right there. And then Q3 is this right here. And then voltage 1, well, voltage 1 is that, as well as voltage 2. And then voltage 3 is given right here. So we've found everything there. Of course, we've kind of did it in a sloppy fashion. Hopefully on an exam or a problem that you have to do, you would do things in order and just get another sheet of paper rather than trying to do like me and cram it all into one sheet of paper. Okay, let's move on and do another problem. Let's say that I have a capacitor that is connected up to a voltage source. And you see that's one capacitor, one voltage source. After a few microseconds or milliseconds, or just very quickly, let's say, this capacitor becomes fully charged. And the voltage across this capacitor is going to be 6.30 volts. Now let's take that capacitor out of this circuit and let's hook it up to another circuit. So here's the capacitor, and let's put it in with a second capacitor, and I'll put a switch down here, and the switch is currently opened. So this is still C1, and C1 is being put into this circuit with the voltage of 6.30 volts across it, so it's fully charged. And then this is C2, and we'll say C2 is 8.95 microfarad. There. Okay, well, I know what the voltage was across this. I know also I could figure out what the charge is. So I could say the charge, let's call that Q0 because that's the initial charge, is going to be C1 times V0. So C1 times V0, that's 3.55 microfarad, multiplied by V0 of 6.30 volts, and that turns out to be 2.2365 times 10 to the negative fifth coulombs. So if I break that in units of microcoulombs, that's 22.365 microcoulombs. So that's the initial charge. That's the charge on capacitor 1 when I put it over here. Well, when I close this switch, when I close that right there, what's going to happen is now a current's going to begin to flow, and capacitor 2 is going to begin to become charged. Now, after a few seconds or milliseconds or microseconds, ever how long it takes, what's going to happen is things are going to settle down, and there's going to be a different voltage than its original on C1, but that same voltage is going to be on C2 because these two are now in parallel. Even if you think they're in series, because this is one loop here, I could put some terminals up here, like there's a terminal going off that way and a terminal going off that way, and it becomes a little more obvious that they're in parallel then. But even if you think of those as being in series, whatever the voltage is across this, it's going to be the same across that, because when you have two elements in one loop, they have to have the same voltages. Okay, so whatever this voltage is, it's whatever that voltage is there as well. Well, the voltage is going to be different than what it was over here, but it's not going to be evenly split because these are different capacitances. You know, C1 is 3.55, C2 is 8.95 micros. So the question is, what is this new voltage over here? So what is the voltage now after things have settled down over here? Well, the voltage is not conserved, so the voltage is not the thing that remains the same in both of these cases. But the thing that is conserved is the charge. Charge is a conserved value. So whatever the charge is over here before, that's got to equal whatever the charge is over here now. And you're going to have some charge that's on C1 plus another charge that's on C2. And that is what is conserved. The total charge before is equal to the total charge after. So charge before was C1 V0. The charge over here is going to be C1 times the new voltage plus C2 times the new voltage, and those two voltages are going to be the same. And that's what we want to solve for. We want to know what V is. So you can factor out V, and you got C1 plus C2. Now solve for V, and you end up with C1 V0 over C1 plus C2. Plug in the values. Let's see, C1 is 3.55 microfarad, multiplied by V0 of 6.30 volts, divided by C1 3.55 microfarad, plus C2 is 8.95 microfarad. Let me do that calculation. and I end up with 1.7892 volts. So there's the new voltage after things have settled down over here. So that's the voltage across C1 and C2 in the end there. Okay, so we finished this problem as well. Let's move on and talk about a slightly different topic, and that has to do with what happens when you put something in between the plates of the capacitor. That something, when you put something in between the plates, is called a dielectric. A dielectric. Now, a dielectric is going to be a non-conductor, so it's going to be something like paper or plastic or glass or silicon. You can even use, liquids like alcohol or maybe oil, some types of oil. But let's say that I have a plate here. That's a terminal coming off of it. And I have a plate over here, a terminal coming off of it. So there's my capacitor. And now I'm going to put a dielectric in between here. And the dielectric would be right up against the plates here. But this is non-conducting material here. Okay, now every dielectric material has a constant associated with it. And that constant is called the dielectric constant. And the dielectric constant is symbolized as the Greek letter kappa. Now it looks like a K, but it's actually a Greek letter kappa, K-A-P-P-A. The kappa value is always a number that's going to be larger than 1. So kappa is always greater than 1. In fact, if kappa equals 1, then that is the special case of the dielectric being a vacuum, which means nothing. So kappa equal 1 means vacuum. There are different kappa values, and there is a table that lists the dielectric constant values for various substances. For example, air is 1.00054. Now notice that air is almost exactly the same as a vacuum. So in air, you don't have much difference in the kappa value. So this would be kappa for air. And you can see it only makes a difference out here in the 4th decimal place. So as long as you don't care about numbers beyond, say, the 3rd decimal place here, then you have permission to use 1 for air. It's not going to make a big difference out until you get out to the 3rd decimal place at least. So a lot of people just substitute air and vacuum and treat them like they're the same. Some other values, for example, paper. Paper has a kappa value of 3.5. Silicon has a kappa value of 12. And look in your textbook, there is a table that lists a whole bunch of values for dielectric constant. Now what happens when you put the dielectric constant in there is that it changes a number of things. First of all, it changes the capacitance. The capacitance values that we've been talking about are technically capacitance values for air. But the capacitance value for air is almost the same as capacitance value in a vacuum. So you would write this as kappa times the capacitance for air. So if you changed out the dielectric and you no longer had air or vacuum in there, then that creates the new capacitance value. So the capacitance value is probably best written this way. It is kappa, whatever the kappa happens to be, times the capacitance for air. So if we have a kappa value that is always greater than 1, then that means the capacitance changes and becomes greater whenever we add in a dielectric between the plates. Now there's something else that it changes as well, and that is it changes epsilon naught. Do you remember epsilon naught? And I said the naught indicates that that's the permittivity of free space. But if we change so that now the electric field is no longer going through a vacuum or through air between these two plates here, then we change it by a factor of kappa. So the new epsilon value, oops, there's no naught there. That's just, imagine that's just a dot. The epsilon value becomes epsilon naught times the kappa. So epsilon also increases in the same way by adding a dielectric in between there. So the capacitance for a, let's say for a parallel plate capacitor, you remember the capacitance for a parallel plate capacitor is written as epsilon naught A over D. A is the surface area of the plate and D is the separation between the plate. But this is what C air is. So if I want to add a dielectric, then this becomes, you change the epsilon value. The epsilon becomes kappa times epsilon naught A over D, like that, which is the same thing as kappa times C air. So you can see by changing the epsilon naught value, you're really changing the capacitance here. You can think of it that way. All right, well, what's going on here to cause such a change in the capacitance? Well, it has to do with the electric fields that are inside the capacitor. So let's say here I've got, this is my plate on that side. Here's my plate on this side. And these are hooked up to wires. And normally if I have a dielectric in here, then there are molecules of the dielectric, and those molecules are not aligned up any way special. They're just neutral atoms. They're not all pointing, they're not dipoles. They don't act like dipoles necessarily, but if they did act like dipoles, they're not all lined up in the same direction. So I have, before I add the dielectric, I have some electric field that goes from one plate to the other plate. Something like that. This is before I add the dielectric. So that creates some initial, let's just call it E naught. That's the electric field with nothing in between the plates. But when I add the plates and I've got my charge on this plate and an equal amount of negative on the opposite plate, then E naught, the electric field, would go in that direction. That would be E naught. And I could draw those all the way down if I wanted to. But now, because the dielectric is there, and there's an electric field there, now these molecules that are in the substance become polarized. So the molecules may do something like this. They may line up like this. In fact, they will line up like this. Now, this is the positive side, so when the molecules polarize, then that becomes the negative side of the molecule, and this is the positive side. Of course, the next one is the negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, like that. Now, if you have a whole bunch of these, all of these are lined up in this way, then above that I'm going to have another negative, positive, another negative, positive. So if I look at just this face, let's say this is the edge of the dielectric here, then that edge of the dielectric has a bunch of negatives on it. And this edge of the dielectric has a bunch of positives on it. So from the face of the dielectric on this side to the face of the dielectric on that side, there's actually an electric field that goes in the opposite direction, like that. So that electric field then, we could call that electric field E prime. Then E total, this would be the total net electric field, is going to be whatever E naught is, and then you have to subtract off E prime. So the net electric field is reduced because of that. So we'll say this, the magnitude of E, this would be E net, is reduced. because of the presence of the electric field. So if E is reduced, then the energy density is reduced as well. So C is increased when we add the dielectric, because kappa is greater than 1, C is going to be increased. And U, the energy, is going to be 1/2 Q squared over C. So the total net charge is unchanged here. Now, I shouldn't say net because the grand total of net charge is going to be 0. So this is just charge on one plate. But because it's Q squared over C, the Q is going to be the same. The C is increased. That makes energy is also decreased. So U is decreased as well. So think about that. By adding the dielectric, you increase the capacitance, you reduce the electric field, you also reduce the total energy. Now let's say that we have just two parallel plates like this. Let's take this space up right here, and we'll draw one plate up there, one plate down here. So there's our area, and now let's put a dielectric in this region right here. But let's do it in such a way that we've got different kappa values, so different dielectric constants. So this is all material that is non-conducting material. This section over here, remember the plates are up here. Let's draw them with some thickness so you can see the plates there. Those are the metal plates. This side has some kappa value. This side has a different kappa value, and this one down here has an even different kappa value. So each of these plates here has an area of A, but we're dividing the areas in half, and this one over here has an area over 2. That's just this portion that's covering kappa 1. And over here is area over 2, so this is covering kappa 2. The distance between here and here, we could say that's 2D, and these individually are both D's. So that's D, that's D. So the entire thing is 2D. Well, how would you treat this? You would treat this like they're different capacitors. That's how you would treat it. I'm not going to work the problem for you, but I want you to recognize that you would have a capacitor over here, followed by a capacitor over here, and another capacitor. So this would be C1, so this would represent capacitor C1. This would be C2, and this represents capacitor C2. And this is C3, this represents capacitor C3, like that. So these two capacitors are in series with each other, and this combination is in parallel with C1. So it would look something like that. Now C1 has this kappa value, C2 has that kappa value, and C3 has that kappa value. Now, given that, you should be able to figure out what one equivalent capacitance would be, and possibly then figure out if this is CEQ, then what is KEQ? Okay, I'll leave that up to you as a problem to work on your own. I think we're going to pause here and next time start a new video on a different subject.